In the last lecture, we determined that temperature is a measure of the mean kinetic energy per molecule of a system. In noble gases, this result is pretty intuitive. The higher the energy, the faster the gas atoms move. This also makes sense if we put two things together at different temperatures. Say I start to make a pot of coffee. The kinetic energy of the water molecules in the steam are greater than the kinetic energy of the molecules in the air. So when they collide, energy is transferred from the hot steam to the cooler air, so the hot steam cools and the cool air gets warmer. On the other hand, the fact that temperature depends only on the kinetic energy of the molecule is perhaps a little surprising because there are clearly other forms of internal energy. It would be very useful to know the internal energy of a system. One way to understand how the internal energy and the temperature is related is to look at the heat capacity. In a heat capacity, the heat capacity tells us how much heat is required to raise or lower the temperature of a substance. So if we put energy in, how does the temperature change? So we're going to start with a monatomic gas, one where the kinetic energy of the atoms is the only kind of energy that the gas can have. The kinetic energy of a monatomic gas is 3/2 kT, or if we are considering a certain number of moles of a gas, the kinetic energy would be 3/2 nRT, where n is the number of moles and r is the ideal gas constant, and T is the temperature in Kelvin. That means if we need to raise the temperature of a monatomic gas by a temperature T, then the amount of energy needed to do that is 3/2 nRT. So the heat capacity of a monatomic gas at constant volume is 3/2 R, so that's going to be in units of joules per mole Kelvin. Notice we have kept the volume constant. What happens if we keep the pressure constant? Well, then the gas will expand as you heat it. So when that gas expands, it's going to do work on its surrounding, and it's going to lose a little bit of internal energy. So the heat capacity of a gas at constant pressure must be larger than a gas at constant volume because of this work done. We can use the ideal gas law, and by setting pressure P to be a constant, we can find that P delta V, which is the work, is equal to nR delta T. So the work done by the gas is nR delta T, and so the work adds a factor of R to the heat capacity. Adding the work done to the constant volume heat capacity gives us the constant pressure heat capacity, which is 5/2 R. I should point out here that if you know the constant volume heat capacity, you can always find the constant pressure heat capacity by adding R. This is interesting because it is telling us that the heat capacity for a constant pressure gas, where it expands and does work, is more than the heat capacity for a constant volume case, where all of the heat is used to raise the temperature. So the heat capacity increases when there is an additional sink of energy that is required in order to raise the temperature. Okay, let's do the question here. So a bubble of 3 moles of argon gas, which is a monatomic gas, is submerged underwater, and it undergoes a temperature increase of 10 degrees Celsius. So how much heat was required in joules? So here, the bubble will expand since it's underwater, and because it's has a constant pressure pushed on it by the surface of the water, this is the constant pressure case. So the heat required is the constant pressure heat capacity times the number of moles times the change in temperature. So that is 5/2 R, so which is 20.8 joules per mole Kelvin, times 3 moles times 10 degrees Celsius, which is 624 joules. Now we'll do the fixed volume case. So here, if this is happening in a glass box with a fixed volume, so that means that the volume is fixed, so we use the constant volume heat capacity. So that is 3/2 R, which is 12.5 joules per mole Kelvin, times 3 moles times 10 degrees Celsius, which is 375 joules. So we notice that the heat required is noticeably larger when the gas expands than when the gas does not have to do work. So what this has told us is that for a monatomic gas in a constant volume process, all of the heat added goes to kinetic energy because that's the only form of internal energy it has. So if we heat the gas from 0 Kelvin our ideal gas will have 3/2 nRT of internal energy. So the internal energy of a monatomic gas is its constant volume heat capacity times the amount times the temperature in Kelvin. If a gas has a different constant volume heat capacity, the work done will still be zero because the volume is set to be a constant, so the internal energy of all gases is their constant volume heat capacity times the number of moles times the temperature in Kelvin. Be careful because we don't necessarily know the constant volume heat capacity of all gases, but if we do know that heat capacity, then we know the internal energy. For example, diatomic molecules like nitrogen, N2, and O2 have constant volume heat capacities of 5/2 R, so their internal energy will be 5/2 nRT. So now we'd really like to know the heat capacity for some more complex gases so we can calculate their internal energy. Well, we already know monatomic gases, so what about N2, right? It's the most abundant molecule in air. That'd be useful to know. The measured constant volume heat capacity is equal to 20.7 joules per mole Kelvin, which is almost exactly 5/2 R. Why is this? Well, we remember that in our monatomic gas, every direction, x, y, and z, contains 1/2 kT of energy, or 1/2 RT of energy per mole. So, in molecular nitrogen, the molecule is diatomic, so it has two atoms bound to each other, and that means that, first of all, the molecule can move in all three directions, and it can also rotate. So it can rotate in two different directions if we consider the atoms to be point particles, so the nitrogen gas has 5 degrees of freedom. If there is 1/2 RT per degree of freedom, then the heat capacity should be 5/2 R, which is exactly what it is. So for nonlinear molecules, in principle, they can rotate in all three directions, so the heat capacity in theory should be 3R, or 6 times 1/2 R. This concept is called the equipartition of energy, and the idea is that on average, the energy in a system of molecules is evenly distributed over all of the degrees of freedoms that are in the molecule. So the energy of each of these degrees of freedom is 1/2 kT per molecule, or 1/2 RT per mole of molecules. So the more degrees of freedom a molecule has, the more ways it has to store that energy, so the heat capacity then increases. So if you add a rotational motion, the heat capacity increases. If you add vibrations, then the heat capacity increases. So this is a very powerful concept, and this gives us extremely accurate results for N2. But what about for some of these more complex molecules? This approximation breaks down. So what's going on? So let's step back a second and reanalyze N2. So there are two atoms in diatomic nitrogen, so there are 6 kinds of motions that are possible. The molecule can move in the x, y, and z direction, it can rotate 2 different ways, and it can vibrate. We've seen that the heat capacity matches 5/2 R, so it matches very well, and it must be a good model for N2, so it must not be vibrating. Well, if we do the experiment very carefully, and we measure the energy required for a nitrogen molecule, the nitrogen molecule will start to vibrate at a temperature that corresponds to about 3500 Kelvin. So, under standard conditions, we get a heat capacity of 5/2 R. For more complex molecules, there's often lower energy vibrations that can be accessed at room temperature, so that means the heat capacity is a little bit larger than the 3R that assumes only translational and rotational motion. Okay, so wait a second here. What am I talking about? What do I mean that it requires energy to make something vibrate? In classical mechanics, there is no minimum energy required to make something vibrate. Sure, if you have an incredibly strong spring, then you may only be able to compress it in an incredibly small distance, but it can't just not move, so what's going on? So this is considered by some to be the first scientific result that clearly refuted classical mechanics. To understand this, we really need quantum mechanics, where there is a minimum amount of energy required for microscopic processes to occur. This was first discovered by James Clerk Maxwell, who's best known for his work with electromagnetic radiation, but he also did a lot with thermodynamics. Maxwell and others struggled with this result, and clearly bothered them. Maxwell is quoted as describing his attitude towards his find here as thoroughly conscious ignorance that is the prelude to every real advance to knowledge. So basically, he knew something was seriously wrong, but he knew his model fit the data, so he didn't really know what was up. So anyhow, you guys have a few questions to answer here, and then on the next set of slides, we're going to start to look at engines.